Soon, America will again send astronauts into orbit and beyond to do what NASA does best: explore.
Okay, so this is the first part, talking about the future of human air and space travel. I believe these could have commercial opportunities for you. The first one, let me see if it works. Okay, so this is actually not space travel, but that's something I would like to do in my lifetime. The future of air travel. I believe most of you are expert in this field, so you should know what exactly it is. This is another view of that. Okay, so the second place, I believe, is the most important, for NASA to explore space and is do scientific research, right? So let's go to International Space Station. I wanted to share. So the reason, International Space Station is different than air traveling is it's in microgravity field. So under microgravity, sometimes people just roughly say zero gravity. So massive physical characteristics, behavior will be different, right? And there's some kind of mathematical therapeutic effect or some kind of manufacturer, some advantages. So that's very important. And I believe, so anything travel to International Space Station after 2030, that's what NASA, extended time of the research and can be commercially destination. And this is another view. So of course, they have a great view at International Space Station. And the next closest, still considered low Earth orbit, is called the geostationary orbit. Sorry about this one. So the reason I share this one is, so NASA is already have a national assets in this location. So what's different? Why NASA put so many assets in this location? If you look at the picture on the left, right, it's a geosynchronous orbit, synchronized orbit. So when you send something on that location, it rotates with the Earth with a fixed, location, one-to-one to Earth. So there's so many advantages. So if you're in that location, you can focus on all your antenna and the receiver. In that location, you can keep a constant receiving, communication information, and also there's so many GPS satellites. We need a fixed location to determine the distance and the time. So this is a good location, and but this is about 22,000 miles from Earth. Instead of an International Space Station, it's only 25 or 24. 240 miles above Earth. So this is another location. NASA already have assets. So there is one theory talking about this location can be used for future commercial traveling, is because if we have a counterweight, if you look at the picture on the right, if we have a counterweight at this 22,000 miles location, right? And because of rotation, of course, you can have a like a straight line. So basically, we can have a so-called elevator shaft. So this is actually made by, instead of made by steel. So we said that with a new technology, we can use a carbon tubing, a carbon nanotubing, somehow the strongest materials in the world. But right now, we only can produce like less than an inch long. But there is advantage for this one. If we do, make a carbon tubing works and do have a counterweight, say we capture asteroid somehow, something capture in that space, so we can, of course, anchored in somewhere in the ocean, right, on ocean platform. So we can ride elevator to anywhere between Earth's surface to all the way to 22,000 miles. And based on the speed, we can make it all the way to the top in 8 days. So that could be of course, you can stop anywhere. So that's another way called a space elevator. But this is still in the concept. But some nations do work on this concept, try to make it practical in 2050. But that's too far away. Another destination is this Artemis moon mission. I know when we talk about the moon mission, we thought about, we have to landing people on the moon. That's actually will take us to 2025 or even 26 because of some kind of contract dispute, some delay. It may be 2026 before the first human crew are landing on the moon. But in the same time, so NASA also built is called Moon's Outpost. So the Gateway is an outpost. Basically, is Moon's space station. Okay, so if that constructed, of course, I believe that could be a destination for commercial, commercial value. Yeah, we can send people there. From the Gateway to landing on the moon, that's something extraordinarily difficult. So, okay, so that's a separate contract. That's called a human landing system. You have a moon lander landing on the moon. So that's going to take much difficult. But at least this is similar like International Space Station, could be useful. And the orbit, is this called near rectilinear halo orbit. It's not a moon orbit, but it's around the moon and easy for Earth to access. Okay, so another location, that's where we send the James Webb Space Telescope there, called Lagrange Lagrange point number 2. So the so-called Lagrange point is the point, gravitational field, say between Sun and Earth. This is a Sun-Earth system. It always have a gravitation field. It's a neutral gravitation field. So if you have any assets in that location, in this case, on the far right, you see that's James Webb Space Station located in that location. It's a balanced, it can stay in that location. So if you look at this picture, so when James Webb functioning, it's actually orbited the sun. It's not orbited the Earth. Okay, it's not like a Hubble Space Telescope. It is only 350 miles above Earth. That's orbited the Earth. While you have to keep the lens fixed on some fixed point is extraordinarily difficult, right? So James Webb take this advantage. It is, it's in the neutral location and it actually orbited the sun. Okay, so can take some great pictures through years. Okay, Gateway, and the next destination will be traveling journey to Mars. We have people complain we already been on the moon. Why we are not the direct go to have a human mission to Mars? There is a difference between Moon and Mars. Go to Moon's mission only take a week, or let's say 6 days. You can just get 3 days, get there, and then you can coming back within a week. If you stay 3 days, we need 10 days. So there's so many things very easy to have people coming back if you have some emergency. If you need some material, we can resupply. But for the Mars mission, it will take 2 to 3 years. It's not just because of distance far. It is because when we sending, say, Mars ship from the Earth to Mars, we try to target Mars and Earth the closest location, which only happens every 2 years once. Okay, the closer the location. So when you get to that location, take 6 months to get to Mars. You know what happens? Earth and Mars become opposite side of the sun, so you cannot coming back. You have to wait. wait another opportunity coming back. So it will take 2 to 3 years. And this gonna make what is a commercial mission a little bit difficult, because you cannot, like a moon's mission, you get to the gateway, you can orbit for a few days, you can coming back anytime, right? But if you go to Mars, you cannot stay in confined spaceship, confined crew module for 2.5 years. You can't. You have to somehow land it on the Mars, and waiting for next turn. Okay, after a year and a half, maybe next turn coming back. So that could becomes a limitation of human space exploration. So now I wanted to explain so why this could be a limitation. Okay, so let me go back. So let's look at the distance between Mars and Earth. If you can see the my arrow. So it's a 1 astronomical unit from the sun. That's the 1 unit from sun. We use this as a standard measure. If you look at the Mars and Earth, the distance is only 0.52, so half of the distance between Earth to sun, right? But if you look at from Earth to Jupiter, that's the next, planet. It would be a 5.2, astronomical. So the distance from Earth to Mars would only 1/8 of Earth to the Jupiter. So what that means for Mars travel will be 2 to 3 years, and for Jupiter will take decades. And for human traveling over that long period of time, physical and medical emergencies, and the food and the water, just in terms of keep human survival, I believe at the current time will be beyond our reach. So that's why in my opinion, the human mission to Mars will be the first human mission to a planet, like cisplanet like Earth, and will be the last mission to landing a human on any planet possible. So I believe this is so important. Okay, so why we have limitations for that one? So I wanted to say, so we're just talking about sister planets. Even to Jupiter could be a limitation for human ever traveling. And but if you look at what about beyond the solar system, between the nearest star system, from the sun is a star system, right? To the nearest one, that's called Alpha Centauri. It will take, if you look at the right side, it will take 4.3 light years in order to traveling at current, in current speed. But if we assuming we increase its speed, or so it will take 80,000 years traveling at 37,000 miles. So in order to get there, so that may beyond our reach with current chemical or solar, thermal, solar or electrical or nuclear propulsion reach. If you look at even further, so the next galaxies, the closest galaxy to our Milky Way galaxies, so the Andromeda galaxies. So that will, if you look at the distance, will take 2.5 million light years. Just in order to traveling to them. So of course, beyond our physical capability, right? So now, so what the limitation is, because of the current propulsion system is all based on, solar powers, solar electrical, or matters. If you look at this chart, it means antimatters, it means chemical propellant or nuclear fuels or whatever, or ion, electron ion engines, right? So all related to need solar lights. Means if you're out of solar system, or too far away from the sun, you may not get enough power, or you run out of the fuel. We have to carry lots of fuel with us. Just like right now, we launch any astronauts to International Space Station. 95% of all the weight is just try to send the human to the location, and everything else will be wasted, right? So because of the fuel, so this is a fuel portion. And for human to survive, you have to carry water, food, and medical and emergency, something. So that's beyond. So now, so there's another part of the propulsion system NASA still try to materialize. One is called a solar sail. So use a solar radiation wave. Whenever you put your palm face the sun and away from the sun, you may feel some pressures, right? Of course, temperature change and some pressures, but very minor. But that pressure could be sent NASA rover, to further distance, more deeper, still within the solar system. And another way, they said that they use laser lights. You have to have a source. You carry laser lights, propelling something, away from sun to farther distance. So these are okay. So now, sorry about it. So why am I on? So I'm gonna talk about this one later. Okay, so this is okay. From now, let me take time. So 2:09. So we may have 10 minutes. So now I wanted to share something new and some insights about physics. Okay, you may not find anywhere in the world. Okay, so I have questions. So for executives of the hospitalities, like executives, so how to motivate a human, what motivates a human to travel, to move, right? So my question for you, what motivate objects, space object to move in motion? And answers? What makes things move? Basically, that's the question. Because of time, so I'm not going to wait for answer. I would just say 99% of people would say, of course, that's gravity, right? So, but I would say, actually, we humans don't even understand what gravity is. The way we under the gravity, like a Newtonian gravity, like attraction force only, every object, as far as them have a mass, they attract to each other. That's what we learn. That's what we know. That's what we believe. Everything in motion is because of gravity. I wanted to say, actually, this is not true. Gravity is not the answer. So we try to discover, so what really gravity is. Okay. So now, people say, well, we already observed that everything's attract to each other, right? That's what Newton says. The fundamental force exists once as long as you have a matter, it has an attraction force. That's what we learn. But if that's true, let's see what happens. Oh, sorry. I'm still learning this new technique. Okay. So if the gravity is the most dominant force and make things move, so what will happen? So everything will be lumped together over the time, of course, right? Over time, lumped together, become a one rigid part. But let's see what we actually observe.
Hubble, the telescope that was supposed to unlock some of the biggest mysteries of the universe. Well, it did all that, and then some.
For example, we've known for a long time the universe is expanding in all directions.
The big question at the time was, how much is the universe slowing down? And the reason that was such an exciting question was because that would tell you how much stuff there was in the universe that would gravitationally attract and slow the expansion.
But asking that question led to one of the biggest surprises of the 20th century. Our universe is expanding at an ever faster rate, under the push of what's been called dark energy.
Dark energy is this pretty mysterious component of the universe. It makes up about 70% of the mass energy budget of the universe. And its strange aspect is it appears to have a kind of repulsive gravity, which is causing the universe to expand faster and faster.
It's actually speeding up. And that's bizarre. That's nothing that we'd expected. And apparently, there's a new entity in the story that we had not taken into account.
And that discovery led to worldwide acclaim in 2011.
Professor Saul Perlmutter, Professor Brian Schmidt, Professor Adam Rees. You have been awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe.
Oh, okay. So I want to say this is basically how we find that observation is different than our perception. Everything attract, but we observed the universe not only not attract like a bigger crunch eventually, but actually expanding. And it's not uniform expanding. So if you have a bomb goes off, you have something break off, you will see every single part, fragment will fly out linear, uniformly in constant speed, constant velocity. However, the expansion universe, so that's what we observe. They are not only the things flying out, so the galaxies traveling away from each other. We observe they are not just uniform away from each other. Actually, they are accelerating. Just like you driving car, if you cruise, you may be uniform or deaccelerating. But in order to accelerating, you have to put your pedal, put the gas in. So you have to have a force. So what the force make the universe expand and does not make the universe crunching together just like gravity says. Okay, so let's see. I try to demonstrate this one. So this is the one video I made. I use my camera made this. Did you see? This is a plasma ball. Has a light filament. I think you all can see that one, right? Did you notice one thing? These light filament, they're almost uniformly, parallelly, evenly distributed around the sphere. So what force made them to distribute evenly away from each other, which is exactly the same force pushing the universe away from each other. And I'm going to use another one. So this phenomena actually related. We know electrostatic, right? What happens, why electrostatic humans here parallel away from each other is all separated? Because magnetic repulsion. When you polarize, when you have electrodes on one side, you just like the plasma ball, you actually, so that's the one, that's a polar, when electrodes that's polarized, this is basically one magnetic pole. Electricity, moving electricity create a magnetic field, right? So one magnetic pole, but if all the filaments started from the same magnetic pole, same pole, what happens? Of course, they are separated because light charge repels. So this is an experiment that I did. That's sorry about that's my hand. So there's a magnet in the leaning tower of Pisa. If you look at it, so I use two. So I have the material here, but because of time, did you see they are separated? So what force made them separated? magnetizes magnetic repulsion. So that's the same force pushing the universe, pushing everything in the universe away from each other. But you say, well, if that's the case, we do observe some attractions, right? But do you have evidence these big objects are aligned to each other? I would say, yes, we do. Okay. So let's see if I can. Okay, so this is one research paper talking about that they measure all the, if you look at the picture here, the light, so these are the axes of galaxies, galaxy axis. They found all these galaxies axes aligned to each other. So why they're aligned? Once you're aligned, when you align something, right, you, of course, you have a center, which have a same pole, and then create on the other end, so create a like pole repel. So that's pushing away. So what I try to say is the universe acting not just attraction, but also repulsion. And where does the repulsion come from? Magnetic repulsion. Okay, so now I wanted to see if I can do some kind of experiment with the rest of the time to demonstrate. And why things in the universe moves, okay? So the first one is called the world, I would say, world simplicity electrical train. Okay, I'm gonna do this one. I hope you can see. I don't know how to, I don't know if you can see my table. So there's a little bit magnetic. So this is a carbon wire. So turn the tube. So what I'm gonna show this one is if we have this carbon tube, and then we have a triple A batteries, and then if I'm gonna looking for magnets. I hope you can see this one, okay? Magnets with a AAA battery. See what happens if I put on the, let's do it again. I hope you can see this one. It's in motion. So what I try to say is everything in motion is because everything made by magnetic particles. So basically everything is a magnet, okay?
Dr. Weiping, are you still
Yes.
there? We need to wrap this up, but this has been very informative. Thank you so much for joining us today. I know you're live. Can we put him on the big screen? Is that possible?
Okay, sure, yeah.
Oh, you're back. Oh, excellent.
Yes. Okay, so because of the time limitation, so I just wanted to say, in order to fall out, everything in motion is due to magnetic behavior. And the reason, we can survive in the solar system, right? Because the magnetic interaction between the object with solar moving magnetic field. So that's why keep the solar system rotates and keep us survive. I just wanted to end my presentation with one conclusion. So everything we know in the world are made by magnetic particles. And the fundamental force is actually the magnetic force. It is the magnetic force make all the things in motion and make life and even consciousness available. So thank you so much.
Dr. Weiping, thank you. And thank you for joining remotely. I know you wanted to make it in person, but you weren't able to make it due to scheduling conflicts. Thank you so much for speaking to us. We could have listened to you for another hour and learned so much that I probably missed in school. But this was very enlightening. Last question to you before we break this up. Is it realistic for us to have commercial hotels in space, maybe near the space station by 2027 as we read the news? Do you think, in your opinion, this is realistic?
2027, because of the schedule. So you cannot rely only on government source. You know, the government has its own pace, right? I believe if you tap in private source and it could available. Yeah, that's something.
All right. So we look forward to welcoming you at the Hettner Conference in 2028 on Space Hotel. And we'll continue the conversation then. Thank you so much, Dr. Weiping.
Thank you so much. Okay, bye.